how's everyone doing? Audio check. Can anyone hear me? Let me know in the chat. Give me a thumbs up. Yeah, I know. Stuff is wild. Awesome, so you can hear me. Cool, cool. Yep, taking it one day at a time. Okay. Let's see. I think there's only a couple of us for now at least, but let's run through some of these. I think we had mostly stuff after number 6 on the multiple choice, and then we'll go from there. We can start from 6, and then I can cover any of the ones that we did not touch on, and we can do any related concepts, and we can make up similar problems to the ones on the practice exam or any similar concepts. So anything from either of you before we get started and then we run through everything? We'll probably only go for no more than a couple hours. All right, let's take a look at this. Okay, so the number 6, that one is just purely conceptual. So number 6 has to do with the strong nuclear force. So there's only one of these. So if you look at this question, it says which of the following statements is not true about the strong nuclear force. So 4 of these will be true and 1 of these will be false. So statement A says the nuclear force has a short range on the order of nuclear dimensions. When you're talking about nuclear dimensions, you're talking about on the order of about 10 to the minus 15th meters. So smaller than the wavelength of light that you're usually using. So that one seems to be about true. The nuclear force, the strong nuclear force specifically has to do with the forces of interaction within the nucleus, which is going to be very, very, very small. So that sounds about right. For B, for 2 protons that are very close together, the nuclear force and the electric force have about the same magnitudes. Now, the thing is that, so the electric force would be the force between 2 protons or any other charges. Specifically because we're talking about the nucleus, we're going to be talking about a couple of protons interacting with each other. Because they're the same kind of charge, they would tend to repel from each other. But now there's the strong nuclear force which holds them together. If that were the same order of magnitude, then what would happen is it would be very easy to pry them apart, but the nucleus is pretty well held together. It takes a bit of energy to pull them apart, so the strong nuclear force is going to be stronger than the electric force. So the one out of all of these that are false is actually B. So the answer to 6, I think, should be B. If you kind of skim through the rest of them, such as the next one, which is affects neutrons and protons, that's true because that's what binds them all together. As you skim through these, the rest of them should be true. So I believe B is the one that is false. Let me know if anyone has any questions on that one. I believe we already did number 7 and number 8 from the previous live stream yesterday. So we'll go past 7 and 8. We can always come back and do similar concepts if we really want to. I think we did not do number 9. So let's take a look at number 9. So for number 9, we have 2 electrons that are propagating in the x direction. The first electron has a velocity which is twice as large as the second electron, so it's moving twice as fast. Which electron has the larger de Broglie wavelength? Okay. So the Broglie wavelength, some value of the wavelength lambda, it's going to be related to Planck's constant and the momentum of the object that we want to discuss. So let's quickly take a look at this on the side. All right. Hello. This was the stuff from yesterday. Okay. So the de Broglie wavelength So de Broglie wavelength has that lambda equals Planck's constant divided by the momentum. Okay. Now, depending on what's covered in the class, this momentum could be put into 2 categories. So if the class covers stuff with relativity, then what will happen is you could talk about like relativistic momentums where the speed of things are very, very, very fast and closer to the speed of light. But otherwise, you would just use the standard definition of momentum. Remember that momentum would otherwise just be a product of the mass with the velocity of the object that we're questioning. So this means that we could say that the wavelength is Planck's constant divided by mass times velocity. So for this question, what we're saying is that for one of the 2 electrons, let's call it A and B, let's say. Okay. So between electron A and B, it says the first electron, let's call that electron A. It has a velocity which is twice as large as the second electron, let's call it electron B. Okay. So let's write that down on the side. Okay, so the velocity of A is equal to 2 times the velocity of B. Okay, so that's the comparison that we're going to make. So what's going to happen is, let's say if we want to find out what happens to the de Broglie wavelength for electron A compared to electron B, we just have to pay attention to this factor that it's bigger or smaller by. In this case, it's 2 times bigger for electron A. So we're going to say that this velocity for A is going to be 2 times bigger in the denominator, but because it's in the denominator, it's going to have the opposite effect or the inverse effect. So that means the wavelength will actually go down by a factor of 2 for electron A. So this will go down 2 times as much. So if I wanted to write something from that, I could say that the de Broglie wavelength of A equals 1/2 that of B. Okay. So that's the statement that we're going to make based off of it traveling twice as fast. Taking a look at this, number 9, let's see here. So our choices are, they both have the same de Broglie wavelength. B and C are saying the one with the higher velocity or the one with the lower velocity has the larger de Broglie wavelength. And then D says electrons are particles, so they do not have wavelengths. immediately, if you just skim the topic having to do with de Broglie wavelength, D is not possible because the whole idea of this is realizing that things that you would normally treat as particles, such as electrons, electrons can actually behave like waves because it's on such a small scale. So we can't say that they're particles necessarily. It's kind of like light, where you see particle and wave-like properties, so the wave-particle duality. We see similar things happening with electrons too. So we can't just say they're particles, so they don't have wavelengths, so that's not true. So we found out that particle A had the higher velocity and had the smaller de Broglie wavelength. So it's going to be the opposite, where the one with the lower velocity, particle B, has the larger de Broglie wavelength. Okay, so the answer for this one would be C. Okay. Let me know if you have any questions on de Broglie wavelength and things having to do with particle and wave nature of objects. You're saying, I know how you feel. Yeah, I know how you all feel right now. Trust me. Okay, let's go down to number 10. Okay, so for number 10, the figure shows two unequal charges. So we have a charge at point labeled W, so over here, and we have another charge labeled at point Y, and we have a positive and we have a negative charge. The negative charge has a greater magnitude. In other words, it's bigger in size. So neglecting if it's positive or negative, it has a larger amount on the negative charge than on the positive charge. Point X is midway between the charges. So this point right here is perfectly halfway between the two charges. In what section of the line, so referencing to this whole axis that spans all the way from the left to the right, what section of it will there be a point where the resultant electric field is 0? So the result electric field is 0. Okay. This question deals with the electric fields of point charges. So we have 2 point charges here, the positive and the negative charge. And we have to remember what the directions of those electric fields are, because remember that you can have 2 electric fields pointing in opposite directions, and that could be a reason for why you have 0 electric field. Another way you could get 0 electric field is by just simply not having any charge anywhere. But if you have charges around, then there has to be electric fields around. In this case, there's 2 electric fields. There has to be a way such that you have 2 electric fields pointing in opposite directions, which are equal in size, and that will cause it to cancel out. We're given a few options here, which is referring to different line segments. So for instance, VW would be the line segment from anywhere from the left side out to the first charge. The next line segment would be to the middle, and then the right half from the middle, and then so on. So let's sketch this out. Let's take this out. Okay. So we have our axis here. We have our positive charge, I believe, on the right side. Okay, so positive Q on the right side. And let's have our negative charge on the right side here. Okay. Let's call this minus capital Q, and let's call this plus little q. Okay. And then let's put a few points of interest. So then V is somewhere over here. W, X, Y, and Z somewhere on the right side. Now, for this, what we're going to write on the side is that the size of the charge capital Q, let me write it actually over here. This charge over on the right side is the larger of the two charges. So this charge is larger than that, so it could possibly have more influence on what happens. Okay, so a good concept that we want to remember here is that for the kinds of charges that we have, positive and negative, the electric fields are going to point in opposite directions. So for the positive charges, the electric fields point out, and for the negative charges, the electric fields point inward to it. So we want to recall. Electric fields of point charges. Okay. So first, a little schematic just showing the directions of the electric fields individually. So outward in every direction, and then inward in every direction. We also have an equation that goes with this that will help us to figure out what will happen to the electric fields if we examine different points. So for the electric field, we have that it's called E, and it's equal to K, Q. I'm just going to use capital Q here, but it could reference to any particular charge in any situation. Divided by r squared, where r is the distance from the charge that we want to talk about in this equation. So the point of this equation in this particular problem where there's no numbers is to help you understand what factors will influence the strength of the electric field. So if you look at some of the factors, okay, K is a constant. That's always going to be there regardless of the charge that you're talking about. So whether if you're talking about the smaller charge or the larger charge, the value of K is going to be the same in both situations for each electric field. So it does not influence if the electric field is bigger or smaller for one or the other because it's a constant. So we're going to practically ignore what K is doing here. But then that boils it down to two factors that affect the electric field. You can make the charge bigger, and that will make the electric field bigger. Or you can make the distance to the charge smaller because it's in the denominator. So by making something smaller in the denominator, it makes the whole fraction collectively larger. So it makes the electric field larger. But you'll notice that the distance is squared, so it has a more stronger dependence on the distance to the charge than the actual size of the charge. So for instance, doubling the charge would only double the electric field. But if you cut in half the distance or use that same factor of 2 on the distance, it actually ends up being squared, so then the electric field goes up by 4 times rather than 2 times. That's another good conceptual question to think about, is what happens if you double this or cut this in half or triple this? How does it affect another quantity in an equation based on what you do to the other things? Okay. So in this question, what you want to do is, if we're going to determine where the total electric field is 0, we need to understand which way the electric fields point at any given section in this picture. So what I'm going to do is I'm going to divide this up into 2 main regions first, and we'll go from there. The first main region will be between the 2 charges, anywhere between the 2, doesn't matter. And the other region will be anywhere outside of the region between the 2, so anywhere to the right or to the left. Okay. The reason I'm dividing this into 2 separate regions is because there's 2 different behaviors that take place depending on which one you're going to do. So for example, if you take the point somewhere in the middle, it could be the middle point or anywhere between the 2 charges. Let's just use the middle point as an example. If you were to draw the electric fields anywhere between the two charges, it would be representative of what happens anywhere between here. Okay, so if we want to draw, for instance, the electric field for this positive charge, we would say that it follows this picture here. So electric fields point away from positive charges. So if you ask, well, which way does the electric field point at point X, for example, then to have a vector that points away from that positive charge would mean that it would need to go to the right. Okay, so notice that drawing this vector to the right, let's call this E plus for E positive from the positive charge. This vector points to the right away from that positive charge. So that matches the description of electric field for a positive charge. But if you also draw the electric field for the negative charge, which we know that electric fields go toward them, you would find that for the same exact point in this picture or this situation, the electric field would have to also point to the right in order to go towards that charge. Let's call this one E minus for electric field from the negative charge. Okay. So because these two vectors point in the same direction, and we're looking for a place where they can cancel, it's not possible here. Okay? Because in order for something to cancel that has direction, you need it to be pointing at least in the opposite direction. Whether if you use the middle point or more to the left or more to the right, you're going to find that both of them are going in one direction. It's not going to work there. The situation may change if you change the types of charges there are. So like you could do it with positive, positive, negative, negative, change it up, and the answer might be different. But in this situation, they will never cancel out anywhere between them. So that eliminates that as an option. So the answer cannot be WX for the line segment, and it cannot be XY. Our options are to the left on this diagram, so VW, or to the right on this diagram, which is YZ. So for this problem, we know that the answer is probably going to be on the outside region, and we have to figure out which one is it, or is it both, or maybe it's none. Let's find that out. So let's take a test point, for example. Let's take some random point somewhere in between YZ. Okay. So just like we picked a random point between W and Y just to see which way the electric fields go, we're going to do the same to the right of the negative charge. If we were to ask the same question, so what's the electric field here from the positive charge? We would say, well, the positive charge is over here, and this point's over here, so the electric field has to radiate away to the right. Okay, so we're going to draw a vector to the right. Call that E plus. Negative charge is on the left side of this point, so the electric field at this particular location needs to point to the left to go towards this negative charge. So I'm going to write that to the left and call that E minus. Okay. Now, as opposed to the middle, the electric fields point in opposite directions. So you would say, oh, if they point in opposite directions, maybe they should cancel now. So the answer has to be YZ. But let's check the other side. So if you do the same thing on the left side for some random point over here, and we repeat the process one more time. Positive charge, but it's on the other side of the point now. So if you ask what's the electric field at this point, the electric field has to point to the left to go away from that positive charge there. Now, if we do the negative charge, electric field has to go to the right to go towards that negative charge. So, electric field to the right, E minus. Okay. Now we have a question that we can't immediately resolve because the answer would appear to be YZ, and the answer would also appear to be VW as well, because they both have a situation where the electric fields point in opposite directions. But that's not the only condition that causes the total electric field to be 0. The other condition is that they need to be equal in magnitude. We've already shown that they're opposite, but we need to show that they're equal. So how do we show that? So how do we know that the electric fields, let me rephrase it slightly, can be equal? Okay, so the magnitude or the size of the electric field that we're trying to show is equal for each of the ones that are opposite in direction. The magnitude is given by this equation for the electric field of a point charge. So we know it depends on two factors. It depends on how large the charge is, and also depends on the distance from that charge. So we need to figure out how these factors influence the electric field for both cases, and then be able to determine from there how they could be equal. So what I'm going to do is, let's start with this right point and let's go through the motions of what will make the electric field bigger or smaller. So if I write, for example, let's call this point on the right side, let's call this 1, and let's call the point on the right 2. Okay. So for situation 1, okay, we're going to ask two questions. Basically, the two questions are going to consist of the factors that we're questioning that make the electric field bigger or smaller. So we're going to ask about the charge, and we're going to ask about the distance. Okay? So let's start with the charge. In situation 1, we have that the charge capital Q is larger than the charge lowercase q. Okay, so we can say, oh, let's call it actually minus m plus. So how about q minus, like that, is larger than q plus. Okay, so we have a statement that says one charge is larger of the two. So what this means for the electric field is, if the charge is larger in the numerator, it makes the electric field larger. So this statement right here tells us that the electric field from the negative charge should be larger than the electric field from the positive charge. Okay. This is our first statement about what the size of the electric field could possibly be. Okay. Now, with this statement alone, it doesn't tell you if it's equal or not. We're going to have to ask what happens to the distance as well. So when we ask about the distance, well, let's look at situation 1. This point is closer to the negative charge than it is to the positive charge. So what I'm going to write is the distance r for the negative charge is smaller than the distance of the positive charge, like that. But we said that the distance has the opposite effect. So the smaller it is, the larger the electric field is. So if the distance to the negative charge is smaller, that actually means that it makes the electric field bigger. So the electric field from the negative charge is larger than the electric field from the positive charge, only based on which is closer. Okay? So we have two statements now, and they both actually say the same thing. So by only looking at the charges, we find that the electric field from the negative charge is larger. By only looking at the distances, we find the same to be true. So the thing is, if these are the only two factors that control the size of the electric field, and both factors tell us that the negative charge creates a larger electric field, regardless of charge and distance, the thing is there's no way that this electric field vector could equal the other one, because these two statements suggest it's always larger. Okay, so the result of these two says that E negative is larger than E positive unconditionally. Okay, unconditionally. So the answer cannot actually be on the right side. But then you might ask, well, isn't it just going to be the same on the left side because it's just mirrored? But that's not quite the case because the charges are different in size, so it's not a perfect mirror. So we have to actually look at situation 2 now. So in situation 2, okay, we're going to go through the same motions and we're going to see if we reach the same conclusion or not. Okay, so in situation 2, at this point on the left side, what is the size of the charges? Well, the size of the charges has nothing to do with my situation 1 or 2 on the left or right side. We said that the negative charge is bigger, period. So Q negative is larger than Q positive, which means that the electric field negative is greater than the electric field positive, again, because it's in the numerator. Okay. So far, we're getting the same result. But what about the distances? Notice that in situation 2 at this point, it's actually the opposite as the other situation. So in situation 2, the distance to the negative charge is actually larger than the distance to the positive charge. So R negative is now greater than R positive. Notice that's the opposite statement from before. If the distance to the negative charge is the larger distance now, that means the electric field is weaker for that one. So I'm going to say that E minus is less than E plus. The difference between the top situation, situation 1 on the right side, and situation 2 on the left side, is that situation 1 is unconditional. There was an electric field from the negative charge always being bigger, no matter what. But in this situation, we have that the charge tries to make the negative one bigger, but the distance tries to make the positive one bigger. So the effects try to fight each other, but there is going to be a balancing point where they do cross and cancel out. So the effect overall of this is that the electric field from the negative charge can be equal to the electric field of the positive charge conditionally. Under certain circumstances, in other words, if you pick the right point in this region, it will cancel out at some point. Okay? So the answer is going to be situation 2, which means that the line segment has to be VW. Now, this topic is really, really confusing and there's a lot of details that go into it. So if you need me to reiterate anything, let me know. Otherwise, give me a thumbs up to let me know that you got this and we're ready to move on. Awesome, got 1 thumbs up. Cool. All right. So, yeah, answer choices. So the answer to this one is VW. That is option A. Okay. Now, what I want you to realize for this one is, like I said earlier, you don't have to have a positive and a negative charge. Okay. I'm going to tell you a couple of ideas that you want to think about if you were to change the charges in the situation. So if you were to, let's say, change one of the charges to the same kind of charge. So let's say if we have a positive charge on the left and we have a positive charge on the right, how does that change the answer? Well, if you think about our diagram and when we made all of the electric field vectors, remember that the electric field vectors were all based on the types of charges we had. So if you change one of the charges to a different charge, what will happen is it will flip the direction of one of your electric field vectors. So ultimately, what will happen in the end is the inside region where you had the 2 electric fields aligning with each other. So if I go back and look at my diagram, If you were to look at this and look at the inside region right here, you'll see that the electric field vectors were aligned, and that's because they were opposite charges. Okay. But if I were to change this negative to a positive, it would flip this one the other way. So we would have a situation where they could cancel out somewhere between the two charges rather than outside on the left or the right. By the same reasoning, if you take the outside regions where they're in opposite directions, they would then become in the same direction. So it would actually become absolutely impossible for it to cancel on the outside. So the answer would be somewhere in the middle, but how you know where the balancing point needs to be, where they actually do cancel, you're going to find that there's a pattern to these problems actually. The balancing point, or the point in which the electric fields cancel out to zero, is the point that is closer to the smaller charge. In this case, it's the charge on the left that's the smaller one. Notice how in our answer we said it was situation 2, where they cancel out to 0. So situation 2 is the side that's closer to the negative charge, or I'm sorry, the positive charge, which is the smaller of the two. If you swap them around and you know which one is the smaller charge, you know the answer has to be closer to the smaller charge, because the only way to compensate for one of the charges being bigger and have the electric fields cancel out is to get away from the bigger charge, which means you have to be closer to the smaller one, and that's always going to be the answer for this kind of question. So whether if they cancel out somewhere in the middle, or whether if they cancel out somewhere on the outside, like this particular problem, the answer is always going to be closer to the smaller charge. Now, yeah, this is why a lot of people have trouble with this problem, is because it's hard to understand why it will cancel out on one side and not the other, despite them pointing in opposite directions. So this one's a very hard one to understand. It takes a lot of time. Okay. Number 11, we have an electron which is moving in the positive y direction. So we have a given direction we'll have to draw in a coordinate system. Moving in the positive y direction at right angles, perpendicular, to a magnetic field, and experiences a magnetic force in the negative x direction. The direction of the magnetic field is in the, and we have a bunch of options here. So immediately, some key phrases to recognize are electron is moving and magnetic field. So when you have an electron or some charge moving in a magnetic field, you should understand that there is a magnetic force, and which has an equation which I'll write out. And there is a direction which is easily determined by the right hand rule, or you can use your left hand for negative charges, or you can just flip the answer from your right hand for a negative charge. So I'm going to erase this, make sure everyone's good. Everyone looks good, so I'm going to erase here. Okay. So let me draw in a little coordinate system. Okay. What you can do with your coordinate systems is one of two things to make sure the coordinate system looks good and works out. First thing you could do is you could draw your standard x and y axis with no modifications. So in other words, you can take, let's say if we draw the x-axis like this, positive is by definition normally to the right, and the y-axis normally will have positive y going up. Okay. If you draw your coordinate system like you would usually draw, with positive x to the right and positive y upwards, what will happen is that your positive z, if you want to imagine that these two fingers and the thumb represent like your coordinate system, so like the index finger could be the x-axis, the y-axis could be the middle finger, and your z-axis could be the thumb. It turns out that if you kind of just line things up, there is a way to actually determine that the positive z must come out of the page, but otherwise you can just remember to do this and just say, oh, positive z is out of the page. So what you can do is you can use the notation where you draw a dot to say that the vector is out of the page, and you can draw an X to indicate that something's into the page. So I'm just going to draw a dot with a circle around it, and I'm going to say that's the positive z-axis pointing out of the page like this. Okay? So if you want to be absolutely sure that the coordinate system works, you can use actually a right-hand rule to do that, and simply going in order from index to middle finger to thumb, it's going to be positive x, positive y, and positive z. So notice that if I were to put my index finger along the positive x-axis and put my middle finger along the positive y, my thumb actually points out of the page, which is what I said the positive z would be in. Okay. You shouldn't necessarily need to do that, but otherwise just draw the coordinate system normally, and the positive z is by default out of the page. Okay. Now in this problem, we have that the electron is moving in the positive y direction. So I'm going to draw an electron here, and I'm going to draw its velocity upward in this diagram, positive y. So let's label that the velocity v. And we know that the magnetic field needs to be found in the problem, but we know the direction of the force that the electron feels. So the force experienced by the magnetic field on the electron is going to be in the negative x direction. So we have that there should be a force to the left in the negative x. Okay. Given that you know the directions of at least two things when you're talking about magnetic force on a point charge moving through a magnetic field, given that you know at least two directions of things, such as velocity and force, or another one is a magnetic field, and given you know what kind of charge it is, you can find the remaining direction, which in this problem is the direction of the magnetic field. There are two methods you can use to find the direction of the missing quantity conveniently. I'll show both of them. So one of them is going to deal with the same setup I've been using before, which is to just use two fingers and your thumb and keeping them normally perpendicular to each other. So when you do this one, the index finger is the velocity, the middle finger is the magnetic field, and the thumb is the force. I'll write that down. So index is the velocity, middle is magnetic field, and the thumb is the force. Okay? And when you use this, you normally use your right hand. You can do one of two things. So again, you can either use your right hand always, and you just have to flip the answer for a negative charge, or you can use your right hand for a positive charge and a left hand for a negative charge. And then you can do this, and it's a really cool sign to give to somebody. So we know it's a negative charge. So what I'm going to do personally is I'm going to use the left hand. So what I'm going to do is I'm going to line it up with the vectors that I'm given. So in this case, I know that I have a velocity that goes upwards. So we have velocity goes up. Now, your thumb and your middle finger may not already align with the remaining vectors, so you need to make sure that it lines up. While the index needs to stay up in the direction of the velocity in the diagram, we need to make sure that the thumb points in the direction of the given force. Right now, my thumb actually points into the page. I just need to rotate it around so that the thumb points in the direction of the force, and the index continues to stay in the direction of the velocity in this case. The remaining one is the middle finger, which points out of the page. That is the magnetic field direction. Okay, so from right hand rule, but except in this case we're using our left hand. the magnetic field points out of page. Okay, so in other words, out of the page would be in the positive z direction. Okay. And again, if you do your right hand, you should be able to confirm the same thing by flipping the answer. So index up with velocity, force to the left with the thumb. The middle finger points into the page, which is the opposite direction it needs to be. So negative charge means it's actually out of the page, which is consistent. The second method is taking your fingers and your thumb like this and keeping it perpendicular to each other. Keep your fingers together. What you're going to do is you're going to point your fingers in the direction of the velocity. So in this case, you would point your fingers upward like this. And what you'll do is, normally if you're given a magnetic field, you would tend to curl your fingers in the direction of the magnetic field. So let's say the magnetic field was into the page. What I would do is take my fingers from the velocity direction and turn them until it matches the direction of the magnetic field. And notice that the thumb stays in the same direction, which is the force. In this case, you kind of have to work off the force and the velocity. And the same rule applies where you use your right hand for a positive charge and your left hand for a negative charge. So I'll do it with my left hand. I'm going to go, force needs to go in the direction of the thumb, and I have my fingers in the direction of the velocity. My fingers will end up curling into the direction of the magnetic field. So in this case, when they curl, they end up coming out of the page, which is the same answer that we got with the other right hand rule. Okay, so it doesn't matter how you do this as long as you're consistent and follow the rule. In this case, gets you that's the positive z direction. Let me know if you have any questions on using the right hand rule, and otherwise give me a thumbs up. Let's see here. So we have positive z direction, so that's answer choice B. So answer to number 11 would be B. Now, I'll also write out a related formula that you may use involving this kind of question. This is just purely using the right hand rule. But if you need to make any calculations, you would also use this equation here. So this would be the force, the magnetic force on a point charge moving through a magnetic field. Magnetic force equals Q, which is the charge, the speed V, the magnetic field B in Teslas for the unit T, and then times the sine of some angle. Okay? When you use this equation with the angle involved, remember that the angle in this formulation is defined to be the angle between direction of the velocity and the direction of the magnetic field. Okay, in most problems, especially in lower level physics courses, a lot of times this angle ends up being 90. Magnetic field being perpendicular to the direction of movement of the charge, so that a lot of times when you do sine of 90, it ends up being 1. So sometimes the equation is just QVB, but it's under the condition that the motion of the charge is perpendicular to the direction of the magnetic field. So just a quick conceptual example, if you have that there is a magnetic field which goes, let's say, left to right. So I'm indicating with the magnetic field lines, arrows to the right, so that's the magnetic field. Let's say hypothetically that you had a charge, and the charge were to move in the same direction as the magnetic field with some velocity. In that case, you would not have any force at all. Okay. If you had a question that said to find the direction of the force on this charge in this picture, trick question, but not really. It's a concept that you need to understand. Because the velocity in this case will be in the direction of the magnetic field, which means the angle between them is 0, meaning the same direction, then the sign of 0 means you get 0 for the answer. So the force will be 0, and there's no such direction for a force. Okay? The same would also be true if you pointed that velocity in the direction opposite to the magnetic field, because then you get 180 degrees, the opposite direction to the magnetic field. Sine of 180 also gives you 0. So as long as it's parallel or anti-parallel to the magnetic field, it won't produce any force. It has to have some angle to the magnetic field that's not 0, 180 to be able to produce a force. This will be the last multiple choice problem on this. Let's take a look at this and we'll play from there. If you have any suggestions of where to go next for probably the next 30 minutes to 45 minutes or so, type in something that you might want to look at, and then we'll go from there after number 12. So for number 12, this one is just simply asking for a particular element on the periodic table. So in this case, you have this nucleus. Okay, the subscript and the superscript 41 and 93, you need to make sure you know what those are representative of. In this case, you want to know how many protons, neutrons, and electrons there are found in that nucleus. The answers here are listed respectively, or in other words, in the same order that it's listed in the question. So for example, 41, 52, 41 would be corresponding to protons, neutrons, and electrons. So when you're looking at these, okay, bottom number is going to be your atomic number. Okay, the atomic number corresponds to the number of protons you have, and that's what gives the element its name is based off of the number of protons. So if it has 1 proton in its nucleus, it's hydrogen. If it has 2 protons in a nucleus, atomic number 2, it's helium. So we know that there are 41 protons, but if the atom is to be neutral, in other words, having no total or net charge, that must mean that there's an equal number of electrons. So 41 protons and 41 electrons. So the first answer and the last answer in this case have to be 41. So that could be A. And actually, that's already enough to determine the answer. You're done. Because there's no other options that have 41 and 41 for the first and the last answer. But let's reason with why it's 52. The top number is the number of particles in the nucleus. So if you have 93 particles in the nucleus, and you know the nucleus is made up of 2 kinds of particles, it's going to be protons and neutrons, then given that you know the number of protons is 41 from the atomic number, all you have to do is subtract 41 off of 93, which gives you 52, and that's the remaining number of neutrons. Okay, that's how you'll handle any of these problems that deal with different elements of the periodic table. Okay. Let me know if there's any questions on this, if you want to see anything a little bit more done out with this. Let's see. I see one comment on Doppler Effect, so we can talk about that. Are you referencing to the Doppler Effect with light waves? I believe that's the Doppler Effect that's covered in 100B. Erase this meanwhile. Let me know if that's the kind of Doppler effect that we're talking about with light, and I believe it's to do with red shift and blue shifting. It's a wave in gigahertz. Okay, yeah, that's probably gonna be for light. Used to measure speed on climate. What do you mean by that? Let me pull this up here. Okay. Doppler effect. How fast is a storm approaching or going away? Okay, I get what you mean now. So it is having to do with light. Okay, so let me take your question, particularly with like a storm approaching or leaving, like you're saying, and let me put it in context to kind of see what's going on with this. Okay, so let's say an example of where Doppler effect is encountered that we see sometimes. So example, let's say that you have radar detecting a storm. Okay, so sometimes, like, you'll see like on apps, on television, etc., you'll have a radar app that shows how strong like rainfall is in any particular location. And so let's say that you have this radar system. Okay. And let's say this is my radar, and it basically what will happen is it's going to emit these waves out, okay? And they travel at the speed of light because they are light waves, okay? So you emit some signal out, and it sends this electromagnetic radiation out, and there's some object or obstacle that it's going to encounter at some point. In the context of, like, for instance, radar in the question that you're asking, most of the time this is going to be used for weather detection, where rainfall is, which way it's moving. This is used actually to help predict where something's going to be at a certain time, like tornadoes. Which way is it going? What is it doing? How strong is the tornado? So it's very, very cool. But let's say you have some, cloud or a storm, and there's rainfall coming out of it. Okay. So sprinkle time. Now, okay, so the storm would have a direction of movement. Let's say in my diagram, it's either going to move in one of two directions to make it simple. Let's say that it could, for instance, move away, question mark, or it could move toward, question mark, okay? One of the two situations. So given that we have this situation, what's going to happen is these light waves will hit the object or the obstacle. In this case, it's some bunch of rain drops and water particles, and they're moving a certain direction. So what will happen is they'll hit it and they'll bounce off and they'll come back to the radar, and it detects the returning waves. But the frequency of those waves, or the wavelength, is not going to be the same. Okay, this is called Doppler shifting. What will happen is, depending on if the source, in this case this would be the source, or if the what's called the observer, which is like your object in this case, depending if your source or observer or both are moving, it could change the frequency that is observed. So what will happen is, if let's say there was someone sitting here and they were observing the light waves come by, if you were running away from the light waves, it would take longer for the waves to pass you. So each wave would pass by slower, which means they happen less often, and that means the frequency would go down. So moving away, conceptually, in terms of the frequency, moving away would cause the frequency observed to decrease. Or if it moves toward the waves, what will happen is the waves will come at the storm, and the observer moves through the waves, and it catches the waves faster. So they pass by each wave faster, so it happens more often. So that's a higher frequency. Okay, so moving toward would imply the frequency observed increases. Okay. That's just conceptually without any equation. You can already tell what's going to create a larger or a smaller frequency. Okay. There is more to this. So for instance, there's a first Doppler shift, which would occur from just the observer moving. But when the light reflects back, there's another complication where when it reflects, the roles swap and the source becomes the observer and the observer becomes the source, and it's a second Doppler shift, and it's a little bit more complicated. But the moral of the story at the end of the day is that the gist of this is moving toward and away from one another has an impact on whether the frequency observed increases or decreases. So for example, some terms you might hear or get thrown around a lot is the term redshift and blue shift. When you're talking about, like, for instance, blue light in comparison to red light has a shorter wavelength or a higher frequency. So there's a bunch of waves happening in a shorter space. So you have something that looks like this. Okay. But then red light, by comparison, might have something that looks like this, where it doesn't oscillate as often. So the wavelength is longer, or the frequency is lower. Okay. So when you're talking about, like, for instance, red shift and blue shift, it's actually referring to, are you intending to increase the frequency, or are you intending to decrease the frequency? So this has to do with higher frequency. This has to do with lower frequency. Okay. So if you want to talk about it in this context, moving away might imply that because the frequency decreases, you could have something like redshift. And for the frequency increase, you could talk about blue shift. Okay. This is actually how we tell which way stars can be moving in the universe. So for instance, if you're sitting right there and you're the Earth, and I'm a star, and I'm moving towards you, okay? What will happen is, if the star is moving towards the observer, then it matches up with a case where you observe a frequency increase, and what will happen is the star will look bluer. And if the star is moving away from the observer, it actually looks redder. So you can tell which way something's moving just based off of what happens to the light that's observed based on its movement. So that could be another potential question to look into if you're looking to study Doppler shift. That's at least conceptually. Let me know if you want more details than that. Otherwise, give me any more questions or topics that you want to cover. Cool, makes sense. Awesome. Let's see here. So we did get through everything on here. Of course, this may not encompass everything. So I don't know how similar your exam is supposed to be or whatnot, but let me know and we can always do another workout problem of any particular topic, or we can talk about any other concept related to any of these. Now the other thing is, I know that some of you aren't gonna necessarily take your final tomorrow. If it were me, honestly, I wouldn't, for a lot of reasons. But depending on when you're taking the final, we could always try to arrange at least one more possible session with some questions that I construct myself based off of what you all want to do. So feel free to email me and let me know what topics you want to see more workout questions for, maybe more multiple choice, and maybe we'll arrange one more time before next week, at least, minimum. And we can do that. So I don't know if anyone has any more questions right now. I think we're all probably exhausted from today. So if you're good, you can give a thumbs up and we could pick up from another time depending when you're taking your final, or you can just throw out any questions you have right now and I'll see what I can do with it. So yeah. And again, if you've been enjoying what I've been doing, then let other people know what I'm doing so that people next semester can find me and I can continue helping them, and I can continue to reach out to more people. And if you want to donate, then links are on my website, including a Venmo and Patreon. So, but I know we're all college students, so. Oh, did she completely cancel the exam tomorrow? Oh, wow. That must have been recent. Oh, wow. Yeah. Well, I think it's honestly for the better. But yeah, I think for most people it'd be a bit of a relief. Let's see here. Okay. I know there's out of all of these questions in the multiple choice, especially the ones I think they're going to be the most confusing or take the most effort are probably going to be number 5. All the stuff with Faraday's and Lenz's law is something people tend to spend a little more time and have trouble with. So Lenz's law and Faraday's law is stuff that we could go over more if any of you still need to brush up on magnetic fields and any of that. Potential and potential energy tends to be a topic that people miss a bit more. So if you're not quite understanding the full gist of potential energy and potential and how they're related to each other, we can do that too. How potential energy increases, decreases. I know number 10 was a very big one, which is why I spent a lot of time on number 10, talking about what happens to the electric fields if they cancel or not. So we could always do another example with that if you want to. So yeah. Again, let me know. Otherwise, we'll just end it if you are all good and we have no more questions for tonight. And then we could just arrange another time later in the week to continue. So let me know or just give me a thumbs up if you think you're good for now. Okay, I'm good for now. All right. And if let's say this then, out of all the possible days between now and next week, are there any strong preferences for any particular days that would work better? And I'm assuming that we'll just keep on doing this later at night. So let me know if you have any particular days that work better than other ones, especially with other finals you may have to think about. Some concepts we could do next time. Okay, so for the next live stream, concepts on 3132 as well. Okay, uncertainty principle, comparing Bohr model and quantum, so equals mc squared. Okay, so using Einstein's equation. Yes. I know that in 31 and 32, so there's a little bit of conceptual stuff on like binding energy, strong nuclear forces, but particularly things that you can do a little bit more with, like short calculations and such, would be binding energy or what's called mass defect. I don't. Did she cover mass defect? It expects you to know that. I think that ties into binding energy as well. I would assume that you need to know what mass defect is if you're going to be talking about Einstein's equation. Angular momentum equation. Angular momentum for what kind of thing in particular? Is it the, we talk about angular momentum involving stuff with like the hydrogen atom and electrons and I believe quantum related things. Okay, let's yeah, we will dig more into that as well then. Yeah, so 31, 32, if you can actually send me like a list of topics from 31 and 32, let me know things such as mass defect, binding energy, strong nuclear force. List off some of those things so I know what things to focus on for the next live stream. So maybe on the next live stream we'll put much more emphasis on 31 and 32. Yeah. Calculating change in angular momentum. Yep. That's kind of similar to calculating the change in energy between different energy levels in the atom. So yeah, all those I think we should talk about and tie together. Maybe I'll make up some practice problems with those too. So. Okay. Yeah, if there's nothing else for now, and it's mainly focused on 31, 32 for next time, then yeah, send me some stuff on 31, 32 that you want to see covered, and we will arrange for some time in the later part of this week. What I'll do is I'll send out another email, but I'm going to drop information on my website as well. So if you go to my website, then again, the live stream information will all be there. And then you can just, again, click the banner at the top of the page. It'll take you straight to the correct live stream link when it's ready. So, okay. With that, feel free to stick around a little bit and ask me more questions. But otherwise, I hope the rest of you have a wonderful night. And please stay safe, definitely. Put your health first and look after others with everything going on. You're very welcome. Anytime, it's my pleasure. And this is a wonderful opportunity that I've gotten to do this. I didn't expect this to be this successful starting out, getting to actually interact with all you and doing this. So this is wonderful, honestly. So thank you for actually letting me give this a test run with you guys. And who knows where this is going to go in the future, but I love doing this either way. So yeah, this is a very, very good test run, definitely. You have a question from her concept questions. Yeah, feel free to copy and paste it. And definitely you're welcome. And then we can take a look at that and see where to go from there. Okay. Let me check email in case anybody has anything they've dropped in emails. Let's see here. Okay. Let's get there. No worries. Okay. You have a uranium nucleus So initially at rest, it decays into a thorium nucleus and an alpha particle. Which one has the greater... I think your question cut off because I think the comments have a 200 character limit, kind of similar to Twitter. So which one has the greater something? Nucleus, the alpha particle, or both the same? Greater momentum. Okay. Okay. So conservation of momentum. So what I want you to think of this as is, if you think back to mechanics and taking a look at systems that have conservation of momentum, a lot of systems you would do would involve like collisions of two objects. Now, you don't have to have collisions. What could happen is, like, let's say you could take something like a firework exploding, and then you take one piece and it splits up into two pieces, and that's the explosion. So conservation of momentum is applied in many of the situations like that. There's a little bit more to conservation of momentum where you apply it. If you dig back through your conservation of momentum stuff, there's a couple ways of looking at it. The simplest way I could probably put this is that it's from Newton's third law, which, if you go back to that, it has to do with forces on two objects interacting will be equal and opposite. Okay. That's where it can boil down to. Otherwise, you can look over to Newton's second law, and it says this when you talk about momentum. So not the F equals ma form of it, but with the change of momentum. Basically, if you have that, and this is referencing to external forces, if there's no net external force or total external force, then if that's equal to 0, then you would have that there is no change in the momentum of the system. And the system could be, for example, two objects that interact with each other. So no change in the momentum of the system, but the term no change ultimately boils down to it being conserved. So the total momentum is conserved, is what it boils down to. So long story short is that this picture kind of follows the picture where it's like you have a firework exploding into different pieces, and they shoot off in different directions. So then they become two halves of a whole, or not exactly halves necessarily. So actually they start from rest, for instance, and they explode into two pieces. That's an example where you have momentum conservation. This problem kind of sounds like that because you have something that interacts with something else. It's different nuclei. Specifically in this case, you have, there was a uranium nucleus and it decays into a thorium nucleus and an alpha particle. So in this one, you essentially, your original nucleus, which is the uranium nucleus, kind of mimics the first picture that I have where the pieces are all still together, and when it decays into the two separate pieces, the thorium nucleus and the alpha nucleus, it's like the two separate things that are splitting off in different directions. So when you have that situation, it's going to use conservation of momentum. So the question was more relating to which one has the greater momentum. So if you're asking which one has the greater momentum, well, let's look at this picture here, just understanding from physics in the first semester. So if you write the conservation of momentum, you may recall that when you say the total momentum is conserved, in other words, it doesn't change, we can say that the total momentum initial equals the total after, or final. So since there's two possible objects you can have, these two, okay, then you would have the momentum of one plus the momentum of the other on one side, and you would have the momentum of one plus the other on the other side. So there should be two terms on each side. Now the thing is that in this context, the two pieces that make up the whole is actually called something different. It's uranium in this case. So when we talk about the momentum of the thorium plus the momentum of the alpha particle, it's really totaling to one piece, which is the uranium. But let's say if I call this, 1 and 2, then the momentum of 1 initial plus the momentum of 2 initial equals the momentum of 1 final plus the momentum of 2 final. So what would happen here is when you use this principle, it actually also states in the original problem that the whole thing is at rest, the uranium nucleus. So if it's initially at rest, which means both pieces are stationary, nothing has momentum, because again, momentum, P, is mass times velocity. So if it's not moving, then no momentum. So the momentum of both pieces in the initial situation, because they're at rest, is 0. So it says now that the total momentum initial is 0, because they're both gone, but it's equal to the momentum of 1 final plus the momentum of 2 final. Okay. With this, if you just solve this by moving something over, it says that the momentum of one of them is equal and opposite to the momentum of the other one. Equal and opposite reaction. That. Okay. So if you ask what's the momentum of the alpha particle, and you ask what's the momentum of the thorium nucleus after it splits or decays from the original uranium nucleus, the answer is that the sizes are actually the same, according to this. The momentum of either one would be the same based off conservation of momentum. Now, that might mean that while the momenta are the same, it doesn't necessarily need to mean that the speeds are the same. So for instance, if you have thorium 238, I think is what it is, 234. Thorium 234 would mean that there's a ton of particles in the nucleus, tons and tons of protons and neutrons. So you have this kind of nucleus, like this. I'm not going to draw all of them, obviously, but you have a giant nucleus full of protons and neutrons, which is the thorium. So thorium 234. And then you have an alpha particle. Now, an alpha particle is just simply 2 protons and then your 2 electrons. So it comes off of it's basically a helium. So 2 protons and 2 neutrons. Okay. So the thing is, if these are your 2 quote-unquote pieces of the whole that break off, the thing is if they have the same momentum, then what will happen is, because one has a much larger mass, the speed of the thorium after this happens would be pretty small, and the speed of the alpha particle, because it has so little mass in comparison to that, it's going to whiz off with a very high speed in the other direction. So hopefully that answers that. Let me know or give me a thumbs up if that was good. Awesome. Cool. On point. All right. I think that probably seems like it's about good for now. So yeah, again, reach out to me by email. It's also listed on my website too if you want to reach out by email. But just let me know the topics that you want to continue emphasizing on next time. So 31 and 32 is going to be a big emphasis, and then I think I got some other emails in regard to some other topics from not 31 and 32, but we will focus more on 31 and 32 since it's the later material that wasn't covered on the exam. So no problem. All right, have a good night everyone, stay safe.